Large language models have undergone an exponential expansion in their sequence lengths. Hardware improvements and memory-efficient attention algorithms have pushed context windows from a modest 2,000 tokens up to 16,000, 32,000, and even past 100,000 tokens. The prevailing industry assumption is that this expansion solves long document processing. The theory suggests that if you pass an entire code base, a dense legal contract, or a dozen search results into a single prompt window, the model can perfectly reason across all that data simultaneously. Empirical testing proves this assumption is false. When researchers evaluate how these models actually process long inputs, they find that the models lose track of information depending entirely on where that data is located within the prompt. This chart illustrates the empirical reality. When we plot a language model's accuracy against the position of the relevant information in its context, we see extreme primacy and recency biases. Models are highly accurate when the answer is at the beginning or the very end of the text. If the target data sits in the middle, performance plunges. This is the lost in the middle phenomenon. Extended context models suffer from the exact same degradation. When we map models like GPT 3.5 Turbo 16K, their accuracy plots overlay the original U-curve. Expanding a modal's sequence length increases its raw storage capacity, but it fails to improve its architectural ability to actually utilize that space. To quantify this effect, researchers established a multi-document question-answering evaluation, utilizing historical queries from the Natural Questions Open dataset. This diagram shows the exact input structure for the test. The prompt contains a single question, followed by a vertical stack of retrieved documents. Exactly one of these documents is the gold text containing the actual answer. The remaining slots are filled with distractor documents, highly relevant text that lacks the specific answer, retrieved via Contriever. The core independent variable being tested here is the position of that gold document. Researchers manipulate the stack by sliding the answer from the very start of the prompt down into the dead center and finally to the end of the context stack. This line chart maps the data from the 20 and 30 document test settings for state-of-the-art models like GPT 3.5 Turbo. As the gold document leaves the extreme top or bottom and hits the middle of the stack, accuracy drops sharply. We can compare this middle position performance directly against the model's closed book baseline. That dashed line represents the model's 56.1% accuracy when it is forced to answer with 0 retrieved context documents. The bottom of the U-curve dips significantly below this line. Dipping below the closed book baseline proves that the distractor documents in the middle of the prompt are actively overriding and degrading the model's own parametric memory. Feeding a language model the correct answer hidden within irrelevant noise is computationally worse than giving it no contextual help at all. The next logical diagnostic step is to isolate the mechanism. Is this failure caused by the complexity of natural language reasoning, or is it a foundational inability to retrieve basic tokens? To strip away natural language confounding variables, researchers introduced the synthetic key value retrieval test. The prompt is a raw JSON object populated entirely with complex random 128-bit UUID strings mapping keys to values. They then scale this synthetic test up to massive prompts containing 140 and 300 unique UUID key value pairs. This chart maps key value retrieval accuracy against the target position within the 300 UUID sequence. While a few models like Claude pass perfectly, models like GPT 3.5 Turbo and MPT-30B still fail. Even for a task requiring 0 semantic reasoning, performance still plummets when the target UUID is buried in the middle of the JSON object. The lost in the middle effect is a foundational retrieval bottleneck inherent to the model's architecture, rather than a failure of logic. To understand why this bottleneck exists, we have to look at architectural constraints, specifically contrasting decoder-only models with encoder-decoder architectures like FLAN-UL2. The core mechanical difference is how they process sequences. Decoder-only models rely on causal attention, meaning they only look backward at prior tokens. Encoders use bidirectional attention, allowing them to evaluate the relative weights of documents simultaneously. When evaluated, encoder-decoder models are robust to position changes. They display a flat, stable accuracy line and show no U-curve, provided the prompt stays within their trained sequence limits. The breaking point occurs the moment the input sequence exceeds the encoder's specific training data limit. When forced past that limit, the U-curve returns. Engineers have attempted to bypass decoder-only limitations with a prompt technique called query-aware contextualization. They place the target question at both the very top and the very bottom of the prompt array to artificially simulate bidirectional awareness. The results of this technique are mixed. While it fixes the synthetic key value test, it has almost zero impact on the complex multi-document QA evaluation. Architectural hacks and prompt duplication cannot resolve the underlying challenge of semantic reasoning in long sequences. We must eliminate one final variable. Does the supervised instruction fine-tuning process unintentionally train models to over-index on the beginning of prompts? This graph compares the QA performance of a raw pre-trained base model, MPT-30B, directly against its instruction-tuned variant. We see two parallel U-curves. The base model establishes the lower curve, and the instruct-tuned model forms a vertically higher, identically shaped curve. Instruction tuning raises the overall baseline accuracy, but the exact U-shape remains intact. This proves the fine-tuning process does not cause the bias. The primacy and recency bias is an inherent effect of causal language modeling over massive, unstructured, long-form pre-training data, such as Stack Overflow threads. The U-curve is an inherent limitation of current autoregressive transformer training, meaning engineers cannot prompt or fine-tune their way out of it. These findings have immediate implications for teams building retrieval-augmented generation pipelines for open domain question answering. A common developer strategy relies on massive context windows to ingest the top 50 or 100 retrieved documents, assuming that higher recall guarantees better answers. This dual-axis graph maps retriever recall against reader accuracy as document counts scale. The recall line scales upward, but accuracy plateaus immediately. Scaling from 20 to 50 documents linearly increases costs, netting only a marginal 1.5% gain. That gap is wasted computational overhead. This forces a new structural approach for RAG engineers. Relying on raw document ingestion is inefficient. Pipelines require aggressive document re-ranking. Relevant context must be computationally evaluated and positioned at the extreme top or bottom of the prompt array, paired with strict rank list truncation to eliminate noise. Building robust AI systems requires optimizing directly for the transformer's cognitive bottlenecks, rather than expanding its raw data capacity.